Our topic today is about pre-stressed concrete. I understand and I know you understand what is the meaning of pre-stressed. All of us learned before that concrete is very strong under compression, but very weak under tension. Concrete cannot support tension. So the typical way or the typical method to overcome this tensile stress to add reinforcement. Do you remember that? If you have a beam like this, and this beam is supported by a column here and another column there, and you have a load or loads on this beam, I believe, or based also on the bending moment, I believe the tension will be at the bottom and the compression will be at the top. So the typical way to overcome this tension, because concrete cannot support tension, I'm gonna add longitudinal bars of reinforcement like this at the bottom of this beam. And we learned how we can figure out the required area steel and how we can figure out the number of bars and what is the size of these bars. That's right. Just give me M ultimate and I can figure out M ultimate divide phi BD square. Then I can use a table to figure out rho. Then I can use an expression to figure out the area steel. Then I can convert this area steel to number of bars and the size. Okay, we have a different technique. Probably I will not use reinforcement. I'm sorry. So how can I support this tension? Okay, let me explain it in a very simple way to understand the concept. We have a column, two columns here, and here is the beam. Okay, all of us understand that we have compression here and we have tension here. We don't need this tension. We need to eliminate. But how? The applied load will cause this beam to be broken like this. So I believe tension will be at the bottom. The typical way to add reinforcement to support this tension. No, we have a different technique. What is your technique? What do you think if I add compression force from this side and the compression force from the other side at the bottom location of this beam? We have compression due to this force, and we have tension due to the effect of applied force from yourself. You are standing here and you cause that tension. So my technique or my new technique, okay, I will add a compression force from this side and another compression force with the same value but in opposite direction. This compression force will eliminate this tension. That means the final conclusion, we have compression here and we have compression here. We don't have tension. Do you think we still need reinforcement? No, no, because the whole concrete is under compression. And the concrete is good in compression, so we don't need any reinforcement. how can I add this compression force and this compression force? This is the meaning of pre-stressing. What is the meaning of pre? Pre means previous. What does it mean? It means you construct this building or this beam. That's right. Before you and your family in your apartment at this location, before this situation, we applied this compression. So your beam is pre-stressed. You applied pre-compression. Before using this building, you applied pre-loading. Coming from this force and this force. This is the meaning of previous, before. So pre-stressing, you applied previous stress on the beam. Then you and your family coming to this building, you applied live load. This live load alone will make tension. But because you have pre-compression, you have pre-stress, this tension plus this pre-compression, the final stress will be compression. Any questions so far? It's a good question. In what case? But before what case, we need to understand what is the meaning of pre-stressed. Okay? Any questions so far? For typical reinforcement, probably this beam span length something around 10, 20, maximum probably 30 feet. As you know, the bending moment diagram M ultimate equal W L square divide 8. So once your L, which is a span length, increased, this L will be squared. So I expect huge increase in the moment. If you have huge number of moment, that means we have huge number of reinforcement. Many bars we need. What do you think if you have a span probably 50, 60, 100? Yeah, we can add reinforcement, but how many? How many? You need probably 100 bars, 200 bars, doesn't make any sense. So we failed. Making this solution is impossible, or making this solution is costly. So the other option, I'm gonna use this technique. I will eliminate the tension and make all of stresses are compression and no need to steel reinforcement. So when I'm gonna use this technique for large span and fast or quickly construction. If you have a bridge, we don't have time to interrupt the traffic. So post-tensioning or pre-stressing beams is the most easy or faster construction technique. Let's go back and understand what's going on. So because of the low tensile strength of concrete, because concrete is very weak, Flexural cracks develop at early stage. We can expect cracking. Steel reinforcement provides the tensile strength that the concrete is incapable of developing. Okay, concrete cannot support the tension. Okay, steel reinforcement will support this tension. However, it is possible to impose an initial state of stress such that when the stresses from the applied load are added, no tensile stress occurs. I can apply compression force from this side and this side. This compression stress will cause pre-stressing here, but compression. When you add your applied load, this applied load will cause tension. So tension plus compression, the final is compression. Once your cross-section, the whole cross-section under compression and compression, I don't care about the value. Compression, 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 I'm good. Concrete is good. No need to steel reinforcement. One more time. The original or the first situation, you have a beam, we have load. That means we have neutral axis. Above the neutral axis is under compression. Below the neutral axis, we have tension. We need to eliminate this tension. So I added this compression force at the bottom. Why at the bottom? That makes sense because you already have tension at the bottom. So I will add this compression and this compression at the bottom. These compression forces will make compression. If you add this one plus this one, so we have compression, we have tension, this compression will eliminate this tension. So the initial state of stress is provided by high strength tendons compressing the concrete. The pre-stressing force keeps all or most of the member cross-section in compression. This is the philosophy of pre-stressing. We need to eliminate any tension, any tensile stresses. Remember, you are talking about huge amount of force. This force will be very high. So we are going to use high strength tendons, something very strong. We have different shapes, different types of these tendons. Sometimes we call it strands. Pre-stressing tendons can be single wire, only one wire, only one, or strands composed of several wires twisted together, like this one, or this one, or this one. So this one can be called strands. Strands mean many wires twisted together to make this strands. Sometimes they are 7 wires. 7 wires strands means we have 1, 2, 3, 4, 5, 6. These 6 wires are twisted around central one. So 7 wire strands manufactured by twisting 6 wires around a larger straight central wire are the most widely used. This shape is most widely used. Can you look to this one? I believe this one is 7 wires. Can you look? So we have central one. How many other wires? 1, 2, 3, 4, 5, 6. So this one is 7 wire strand. Strands come in 2 grades, 250 KSI, 270 KSI. Guys, can you imagine the strength of these wires or these strands? Okay, I can explain it to you to imagine. Anybody can remind me what is the meaning of this diagram? Do you remember that? Do you remember this diagram? We learned it in the first week in this course. Thank you. Thank you. Stress strain curve. Stress strain curve for steel. If you have a steel bar under tension and you are measuring the force and the elongation delta, you can construct this diagram, and we covered this before. Just to let me imagine, anybody can remind me what is the value of F yield? I believe in our course, our F yield probably 40,000 PSI, 50,000 PSI, 70,000 PSI. If you would like to get it, KSI 40, 50, 70. I'm sorry, 60 KSI. So the maximum or the strongest steel reinforcement that we learned was 60 KSI. But you are talking about strands with ultimate capacity 250 and 270. That means you are talking about value here 250 or 270. Do you think this steel reinforcement is strong like this one? No. We have a very strong material. Strands, the maximum, the grades 250 and 270 KSI. The grades for the maximum steel reinforcement, the strongest one was 60. 60. So please compare 60 to 270 to imagine what is the strength for these wires. What is the strength for these strands? Did you imagine? It doesn't matter. All of them or one of them. I don't care about the cross section. I don't care about the cross section. The material, I'm talking about material. I'm talking about material for strands and material for steel reinforcement. I don't care about what is the cross section or how many wires. No, this is not my problem. I'm talking about material. Okay. So you are talking about a very strong material, a very strong element, because this element will be loaded by a huge amount of force. So it's dangerous. Be careful. Anyway, so where I will put the tendon. Tendons will apply compression on concrete, and that makes sense for me. That means tendons must be at the tension site in concrete. For example, we have a beam to span. Do you remember that? The bending moment, which is drawn at the compression site, that means at this location, compression will be at the top, tension will be at the bottom. That makes sense. We expect here tension. So your tendon will be at this location. At support, compression at the bottom, tension at the top. So we expect the tension here. So your tendon will be here. At the other side, compression at the top, so tension at the bottom, so we expect tension here. So the tendon will be here. So I can put the tendon profile looks like this. Why this shape? Because I need to pass through any tension in the beam. That makes sense? That makes sense for you? It's very important. It's very important because you are applying this compression force to overcome the tension. Doesn't make any sense to put this compression force at the compression. So compression plus compression, you will make this beam to be failed. We need to overcome the tension. So the sense is to put these tendons with a profile looks like parabola, looks like triangle, looks like trapezoidal shape, anything, and I don't care, to overcome the tension. So please go ahead and figure out where is your tension. I can decide what is the profile of this tendon. How can I figure out the tension? You learned this before. Go ahead and draw your bending moment diagram. Bending moment diagram is drawn at the compression side. If you can figure out where is the compression side, I can figure out where is the tension side. We learned this before. We have two techniques of pre-stressing. One called pre-tension and one called post-tension. By the way, pre means previous, before. Post means after. Before or after what? Pouring of concrete. So for pre-tension, the tendons are pulled to the specified tensile force before placing the concrete. Then concrete is poured around the tendon. After the concrete reaches the specified strength, probably after 7 days or 14 days, the tendons are cut at the anchorage. The compressive stress caused by the shortening of the wires, because these wires looks like a rubber band, would like to go back. You are stretching them, you are pulling them. After cutting them, these strands would like to go back. So you can expect compressive stress. Okay? The other technique, no. The tendons are free to slide within the member inside tubes, sheath, or conduits. After the concrete hardens, we pour the concrete and we are waiting for 14 days or 28 days without pre-stressing. Then I will place these tendons through these tubes inside concrete and try to jacking them. Then tubes may be or may not be subsequently grouted to be bonded to prevent corrosion. The tubes can also be filled with corrosion resistance grease. I will show you two videos. Let's start with the first one. Show you what is the difference between pre-tension and post-tension.
Order yourself a nectar now. You'll get $399 worth of accessories. $365.
Okay, thank you.
Pre-stressed concrete. In case of big concrete construction projects like bridges, steel reinforcement bars alone won't be sufficient to provide the necessary tensile strength. In this case, pre-stressed concrete is being used. In pre-stressing, the rods or tendons are stretched along the axis and cement is poured. Later, when the tendons are released, the compression is generated at the bottom, which tries to counterbalance the compression due to loading at the top part of the beam. The principle behind pre-stressed concrete is that compressive stresses induced by the high-strength steel tendons in a concrete member before loads are applied. This will balance the stresses imposed in the member during the service. Pre-stressed concrete can be used for the construction of roofs, floors, walls, and bridges with longer unsupported spans. Pre-stressing is generally done by two methods: pre-tensioned concrete and post-tensioned concrete. Pre-tensioned concrete. Pre-tensioned concrete is those in which the tendons are tensioned before pouring of concrete. The tendons are initially tensioned and anchored at both ends, and then concrete is poured over it and cured. When the concrete attains desired strength, the tendons are released and projections are cut out. The pre-stress imparts into beam through bond action. Post-tensioned concrete. In post-tensioned concrete, the tendons are tensioned after the concrete is poured. Initially, the concrete is cast around the sheathing. The ducts are formed in concrete in which tendons are placed. After the concrete is hardened, the tendons are tensioned by hydraulic jacks and anchored. In case of bonded type tendons, the duct is grouted with sufficient slurry. In the unbounded type of tendons, grouting is not necessary. We will learn about this later. Thank you for watching. Stay tuned. The best is yet to come. Kindly.
So we have two types of pre-stressing. Pre-tension, you are pulling the tendons first, pouring concrete, then cut the tendons. The second technique, post-tensioned. You need to pour concrete first, but before pouring concrete, you have to locate, you have to put tubes or sheath or conduits inside concrete. At the location, you need to put tendons. Then pour concrete and wait for many days for full strength of concrete, curing all of this stuff. Then you need to pass the tendons through these tubes and then apply post tension, and then probably apply grouting or corrosion resistance grease. The second video will show you the techniques used in constructing a bridge.
Step 1. Install soffit formwork.
Formwork.
Install site formwork. Step 3. Install reinforcement.
Reinforcement. These reinforcement are minimum for shear, for torsion, for shrinkage, not main steel reinforcement, because the main steel reinforcement will be we will not need this reinforcement for tension. We need reinforcement for another issues like torsion, like shear, like shrinkage, like creep.
Step 4. Install brush-hair for tendon profile. Step 5. Installation for post-tension duct.
Here is the duct. Here is the tube. It's not a tendon. No, it's a tube. plastic or PVC or something like this, any shape.
Step 6. Push strand into duct and install anchor plate with spiral reinforcement. Step 7. Complete install of every tendon. Step 8. Complete side formwork. Step 9. Complete end of formwork. Step 10. Concreting. Step 11. Install anchor.
Then applying the post tension. Guys, if you pull these tendons, we need to put anchors. So anchors is critical.
Head and width. Step 12. Tracing. Step 13. Cutting end of strand. Step 14. Install anchor grout cap. Step 15. Grouting.
As you remember, we have duct and we have tendons inside these ducts. So we need to fill these ducts around the tendon with grout. Grout means something looks like cement with water only. If you mix cement with water, looks like grout.
Step 16. Remove grout cap.
So here is the pre-stressed beam. This beam is pre-stressed. Then this beam, in few days or few hours, we can construct them for bridge span between this column and this column. So this bridge called pre-stressed concrete. You are preparing your beams in a different site. Then by a crane, you can lift them and put them between supports in few hours. Okay, any question? Before continuing, I would like to explain what is the effect of this pre-stressing. Here is the beam, and you put the tendons at the bottom. These tendons will apply compression at this location and the compression at this location. What do you think? This compression force or this compression force will cause something called camber. Or uplift deflection. That makes sense. If you have, I will not say piece of wood, but if you have something weaker, if you push it from the bottom, I believe you can expect camber. So we have vertical deflection, upward deflection. We will cover it next time. Upward deflection. And also, this deformation will cause, we have compression at the bottom, and probably we have tension at the top, and that makes sense. So I'm talking about the effect of pre-stressing only, without on weight, without live load, without anything, just pre-stressing force. If you apply compression at the bottom of the beam, you can expect this deformation, and you can expect compression at the bottom, tension at the top. I will talk about this beam without pre-stress. We have dead load and we have live load. Can you tell me what is the expected deformed shape? Right now I'm talking about external loads only. dead load plus live load only, without pre-stress, I believe this beam will deflect downward like this. We have vertical downward deflection. And we expect tension at this bottom fiber, and we have compression at this top fiber. That makes sense? Okay. Because we have both of them together, we have pre-stressing and we have external load. So please add them together and tell me what is the final shape. What is the final shape of deflection? Do you like, I'm asking, do you like the final shape of deflection to be upward or to be downward or to be zero? I'm asking, what do you like? Zero. Omeri said zero. So any answer? Any other answer? I think to be upward, the final shape, to be upward doesn't make sense for me, because if you are walking with your truck on the bridge, doesn't make sense the bridge is cumbering up or the deflection is upward. Doesn't make sense for me. So I believe upward deflection doesn't make sense. So my question is, do you like to make it zero or a little bit of downward deflection? Zero Umeri, zero Burak. You need to think. Guys, I told you, the first case, we have pre-stressing only. So we can expect upward deflection. We can expect compression at the bottom, tension at the top. After we add dead load and the live load like trucks, cars, pedestrian, all of this stuff, people, all of this stuff, live load. So dead load means on weight, finishing, asphalt layer, all of this stuff. So dead load plus live load will make or will cause alone will cause downward deflection, tension at the bottom, compression at the top. I'm asking the final deformation. Do you like to make the final deformation to be upward or zero or downward? A little bit. Downward, a little bit. Upward, a little bit. Zero, zero. Why, Omeri? Why slightly downward? Slightly downward is correct. But why? Any answer? Okay. Guys, if you this post tension, how much? How much? If you apply high level of pre-stressing force, you can expect too much of upward deflection. If you apply small value of pre-stressing force, you can expect small value of upward deflection. So the level of pre-stressing depend on the level of pre-stressing, you can expect the value of the deflection. No. Okay, listen to me. Everybody, listen to me. I will assume I applied pre-stressing force equal 10 kip. This 10 kip will cause upward deflection 0.5 inch. And the dead load plus live load will cause down 0.5 inch deflection. So this level of 10 kip, and if you have dead load plus live load, all of them together, what is the final deflection here? Will be 0, because you designed your pre-stressing force to cause 0.5 inch upward, and the given load, dead load plus live load, will cause downward deflection 0.5. So the final deformation will be 0. That makes sense? I have a question. Okay, Omer, I'm not sure, Brock, I'm not sure you are, Omer will be slightly more than our force. No. Guys, do you think life load on a building or bridge exists all time? Sometimes we have a traffic jam on a bridge. Sometimes we are at midnight, no cars, no trucks, no life load on the bridge. So if the dead load and the life load together make 0.5 deflection, and this 0.5 balance with this 0.5 under the effect of pre-stressing, probably if you don't have life load, and that makes sense, probably we don't have life load on the bridge. There is no cars, no trucks. We are at midnight. Everybody's sleeping. So dead load alone will cause only quarter inch deflection. But the pre-stressing will cause upward 0.5. And the dead load alone will cause downward 0.25. The final shape will be upward. We don't like this. We don't like upward deflection. That doesn't make any sense. So during the night, we can see the bridge to concave up. Doesn't make any sense. What makes sense for you, okay, I will put here pre-stressing force to cause upward deflection for 0.5. I'm sorry, for 0.25 only. For dead load plus life load together will cause downward deflection 0.5. So the final shape after you add pre-stressing and the applied load will be downward deflection. How much? Quarter. For any reason, we don't have life load, okay, that means the final deformation for this one will be 0, or will be a little bit close to 0. Okay, so this is the meaning of this slide. Limitation. we have limitation. When a live fluid acting on a beam is a large fraction of the total load, you have a very huge number of live fluid, but acts not all the time. It may not be possible to design the beam so that it has no tensile stress or deflection under full live fluid. We need to design for dead load, and we need to understand that this live fluid probably is not exist. So high pre-stressing, be careful, because probably you can apply high pre-stressing required for full live fluid. You are assuming that the live fluid is full, and then you choose this high level of pre-stressing, but make sure, because the live fluid is not present, then the beam deforms upward excessively. It's not good. Very large pre-stressing force may also produce enough axial shortening. This force and this force will cause shortening of this beam. I'm not talking about immediately, I'm talking about on the long run, after 5 or 10 or 15 years. This shortening will make release for the pre-stressing force. So be careful about pre-stressing force to overcome the whole live fluid. Doesn't make any sense, because live fluid sometimes does not exist. So the scenario is you are designing pre-stressing to overcome the dead load. Okay, dead load all the time exists, but for live fluid, no. Losses. When you apply pre-stressing and you are using the structure, we expect losses. So by the hydraulic jack, you apply initial force here 10 kb. This level of force will not continue, because this 10 will be decreased a little bit, will be 9 or 8.5. Why? Because we have losses. We have different type of losses due to the effect of tendon seating, creep, and shrinkage in concrete. Shrinkage means water is coming out of concrete, so we can expect shrinkage. Decreasing in the volume of concrete, that means losses or decreasing in the pre-stressing force. Elastic shortening of the member, movement of the anchors, relaxation of the steel tendons, friction between the tendon and the tubes around the tendons. All of these reasons are sources of losses. So we have initial pre-stressing, and we have final pre-stressing. Initial pre-stressing just after releasing, after release. Final pre-stressing under the effect of surface load. After 1 year, 2 years, 5 years, 10 years. In between, we have losses. These losses, probably for this reason, or this reason, or this reason, or this reason. So we have Fi and we have F. Fi, initial pre-stressing force, F, final pre-stressing force. Any questions so far? Any questions so far? I just covered an introduction for pre-stressing. We still have 3 parts with 3 problems. The first one, we need to calculate the stresses due to the effect of applied force and the pre-stressing force, and tell me what is the final stress, because the final stress must be compared to the allowable stress according to ACI. Once your allowable stress is okay and your stresses is safe, second step, deflection. Your pre-stressing will cause upward deflection. How much? You need to calculate it. What is the value of deflection? And what is the value of deflection due to the given load? Then I will add this one and this one to get the final deflection. This is the second part. The third part, we need to design the cross-section ultimate design to give me what is the design moment strength. What is the design strength of the cross-section with pre-stressing force. So we have 3 different parts with 3 different problems. In this topic, I will start with the stresses. This one is very important. Very important. You have to understand it. So I will cover it next time and see what are the allowable stress according to ACI and how we can calculate these stresses.